This conference will now be recorded.
This is Math 211, Section 1.8, Continuity. We had a few examples from this section that we skipped over in class, starting with example 2, which says to graph this piecewise function and state the intervals of continuity. Remember, continuity means that we can essentially, in everyday English, that we can trace the entire function without lifting a pencil. So we're wanting to know if this piecewise function is continuous or if it has any discontinuities. So the first thing that we want to do is we want to break this up into the pieces that we need to graph. So I'm just going to draw a rough sketch here. So we have our xy axis. And the first function says we're going to graph y equals cosine of x if x is less than 0. So remembering from trig, we know that cosine of 0 is going to be positive 1, but because there's no equal to here, we're going to put that as a open circle. And then remember that cosine of x follows the wave pattern. So as we start heading this direction, we have our negative pi over 2, our negative pi, negative 3 pi over 2, and negative 2 pi, because remember we're going to the left of 0. So cosine goes down, continues down to negative 1 at negative pi, and at negative 3 pi over 2 it is back at 0, and at negative 2 pi it is back at 1. So I'm just going to use those extra points to help me rough sketch in cosine of x. And again, it's hard to draw with these pens, but there you go. There's the wave for cosine of x. This says our second function is that y equals 0 if x equals 0. So we are looking at a singular point there. I'm going to do that one in a different color, so I'll mark here. This means that we're filling in the point 0, 0, so we need to put a closed point there. Next, we want to graph the third and final function, so I'm going to do it in maybe blue. We have y equals 1 minus x squared if x is greater than 0. So this is going to be a blue line. That is a parabola. You can kind of rewrite this. So this has, using transformations of functions, this is shifted up 1 from the vertex, and this is a reflection over the x-axis, which means it's an upside down parabola. If you don't remember transformations of functions, obviously you'll want to review that video. There's one in the Math 136 link that I gave you guys for previous knowledge videos, but you can also do a table of values as well. So if you want to plug in 0 here, that gives you 1, which makes sense, that's this point, but it's also not going to be closed in because there's no equal to. And if we plug in positive 1, we get 1 squared is 1, minus 1 is going to make that negative 1, so that's going to be plus 1, that's 0. So just getting that extra point there, and we know it's a parabola. So this is kind of the graph, the rough sketch of this graph. I could draw this graph completely except for at x equals 0. We have a discontinuity there. So we would say that this is continuous on negative infinity to 0, unioned with, let me get my eraser. Remember, union is a U symbol, 0 to infinity. Notice we're not including 0, we're not continuous at that point. So this is a discontinuity. All right, and then we did example 3 in class. We did not do the intermediate value theorem, so I'm going to go through that and walk through it with you. It says that suppose a function f is continuous on a closed interval ab, and let n be any number between f of a and f of b, where f of a does not equal f of b, so in other words, they're not the same y value. Then there has to exist a number c in the interval ab, open interval, such that f of c equals n. For some reason, the graphic for this did not show up, even though all my other graphs did. I'll try to reload that. Essentially what we're saying here is that if you have a height n, here's 0, and you have a function that one of the points, let's say this is a f of a, is got a y value that's below n, and let's say that another function point is b, f of b, and notice it's above n. That means if this is a continuous function, somewhere along here we had to have crossed that line y equals n. So that means there would be a point c, f of c, where f of c is the value n. So that's essentially what the theorem says. To show that there exists a root of a function, so a root, remember, means that your y value equals 0. When it's continuous on an interval, we only need to show that one endpoint has a positive output value and the other input has a negative output value. That doesn't tell you exactly how many roots there are, it just tells you that there is one. And even if you got like 2 positive values in your interval, that doesn't necessarily mean there's not a root, it just means that this test is inconclusive. It only proves that there exists a root if the sign value changes for that output value. So essentially we're saying n is kind of like the x-axis here. We're letting it be the x-axis, which has a y value of 0, and so we're looking for something that's positive and something that's negative to prove that there exists the root. So this is the function that I came up with for this one. It's 2 over x equals x minus the square root of x. And we want to plug in, the interval is 2 to 3. Remember, this is not an ordered pair. This is the x value at the first part of the interval. This is the x value at the ending of the interval. So if we plug in 2, we get 2 over 2 equals 2 minus the square root of 2. That is 1 equals 2 minus the square root of 2. I would probably solve that over, so that's going to be 1 minus square root of 2, which we just need to know, is that positive or negative? Square root of 1 is 1, square root of 2 is going to be bigger than 1. So you're actually, it's about 1 point, I can't remember, I think 4 something. Anyways, it's bigger than 1. So if you subtract it, you're going to get a value that's less than 0. So this is going to be a negative y value. And then if we plug in 3, this is 2/3 equals 3 minus the square root of 3. I would multiply everything by 3 to clear out that fraction. And then divide everything by 2, or sorry, subtract over the 2. So that's 7 minus 3 on the square root of 3. And we just need to know if that is bigger than 0. Now, these didn't come out to nice ones because I didn't pick a polynomial, so I'm going to check this one. So 3 square rooted is about 1.7 something times 3. And that comes out to 5.196. So if we subtract that from 7, we would still be positive. So that is going to give me a positive y value. So by the intermediate value theorem, we know there exists a root of the function between the interval 2 to 3. We don't know if there's just one or if it's more than one. We just know that there exists one. All right, that's the end of the 1.8 section.